So next paper is Asymmetric Memory Pool DoS Security, Formal Definition and Provable Security Design. This is from our group in Syracuse University. Presenter is Wan Ning. Wan Ning, you have the floor.
Hello. Okay. Good morning. It's a great pleasure to have the chance presenting our work here. Our work is about asymmetric memory pool DoS security, and I'm Wan Ning from Full Stack Security Lab at Syracuse University. And this work is collaborated with my advisor, Dr. Yuzhe Tang, and my labmate, Yibo Wang. Our talk includes the introduction, security definition, design, and evaluation. And the proof part will be presented in the poster. Let's have a brief review of the transaction lifecycle in blockchain. The user will create a transaction and it broadcasts to the network. Then the validator stores the transaction in the memory pool and they select the transaction to build a block. When the block is confirmed, the transaction is finalized. And this process is adopted to most of the blockchain systems like Bitcoin and Ethereum. Now we see the memory pool is a buffer of the unconfirmed transaction. But what if it is out of service? Then the validator gets no revenue and the user can't trade. And the previous works show an arms race between the attackers and the code designer. The first generation attacks are in one step, like deter and mempurge. Then the quick code patches are added to mitigate those attacks. Then the second generation attacks are stealthier, with multiple steps, like NP-fuzz. But how could we end this race? We need a provable defense, and that's what our work achieves. Next, I will introduce our security definition. Here is a simple example for the eviction attack. The benign user sends transaction 0 to the memory pool, and the validator selects the transaction 0 and execute it to generate a block. Then they can get the revenue. But attacker sends an adversary transaction 1 before the block generation. And this transaction 1 is invalid and evicts the transaction 0. Now the validator can only generate an empty block with no revenue. And the normal user is unhappy because their transaction is excluded. Now let's say we have an attacker. His capability is to send 2 adversary transactions. In this case, transaction 1 comes first, then transaction 2. And the state changes from S to S12. And the final state revenue drops to 0. And the attacker can send them in a different way. Transaction 2 comes first, then transaction 1, and the state becomes S21. For either of these cases, the attack is successful if the revenue finally drops to 0. So to have the security definition, we need to mitigate all these cases. Then we have the definition as below. For any final state, S12 or S21, we have a lower bound for the total fees in final state, and which is depends on the initial state S, and denoted as GS. But here's the challenge. We can't know the execution order when the transaction is coming to the memory pool. So we use the price to estimate the lower bound instead of the fees. Now we have the designs to meet our definition. First, the memory pool has 2 transactions, 1 and 2. Then the transaction 3 comes. And at the right side, we have our transaction detail. The 1 and 2 are from Alice with nonce 1 and 2. The price is 1 and 100. Then transaction 3 is from Bob with nonce 1, price 10. And we have a baseline policy. It admits transactions only based on their price, called price-only policy. In this case, transaction 3 is now evicts transaction 1 because it has the lowest price. And transaction 2 will become a future transaction and is invalid. So the total price will decrease from 101 to only 10. That's not secure enough. So we asked, what if a more security aware designer do? Then we proposed a better policy called ancestor minimum price. This price gives every transaction a score. And this score is calculated as the minimum ancestor price. For this example here, transaction 2 will have the score 1 because its parent transaction 1 has the price 1. And for this policy, it will evict the lowest score transaction. And this transaction should be a child. So in this case, the transaction 3 will evict transaction 2 instead of transaction 1 now. And the total score now increases. To take it further, we have 2 transaction graph model. And for both cases, the total score now is increasing. And to see the final state here, the total price is never less than the total score. So we have the lower bound for the final state total price. That is the total score in the initial state. And that meets our definition of the security. At last, we evaluate our designs. We retrofitted our gas to implement our policy, AP, and we reply the eviction attacks on them, and we report the validated revenue over 90 blocks. And in the figure, we can see when there is no attacks, the AP have the same revenue as gas. But under the attack, the gas is unsecure because the revenue decreased to 0. And our policy mitigate this attack because the revenue is not decreasing. In conclusion, we have the economic security definition for the public memory pool, and we present the first provable economic secure memory pool design. Then we have the proof, and we implement the design on the real-world client. And thank you for listening, and welcome to our poster if you have any questions.